And, all right. So, good morning, everyone. Let's get started. Okay, so last time we talked about the hypothesis testing, and I hope you still remember the two examples I gave you, and hopefully that those examples can help you better understand what is going on when we do a hypothesis testing. So basically, when you try to answer a biological question, for example, if you for any of your dissertation project, you're going to start from a question, right? You want to address that question, then you need to form two competing hypotheses. One is the non-hypothesis. The other one, of course, it is on the other way, right? The alternative hypothesis. All right. So basically, based on your non-hypothesis and the alternative hypothesis, so in statistic language, you can form two distributions, just like the slides shown here. So you have like one distribution, which is based on your non-hypothesis. So here we just for simplicity, so for a simple example, suppose we are interested in testing the population mean. So once you have a non-hypothesis, which means like your population mean equals to mu zero, then based on your non-hypothesis, you have a non-distribution, right? So the same if you have your alternative hypothesis, which means like your population mean is equal to this, which is completely different from the mu zero, then you have another distribution, alternative distribution. All right. So what we do in the hypothesis testing is we don't test both of them. We just put the non-distribution on a trial, right? So, okay. So once you have your non-distribution, then you have a ruler, you have a measure for the testing. So suppose based on your non-hypothesis, you can collect some data from your experiment, and based on your data, you can calculate the so the data, we call the data as a sample, right? So based on your sample, you can calculate a sample mean. If your sample mean is somewhere here, which is close to the mu zero, then you have a good reason to believe your null hypothesis is true, right? So you're gonna accept your null hypothesis, and that's it. However, if you got a sample, and based on your sample, you calculate the sample mean, and the sample mean gives you a value like here, so like this value here, and which is very far removed from the mu zero. So this is the mu zero, and this is the mu alternative, right? So based on your sample, you got a value, sample mean, which is very close to the mu A rather than the mu zero. So this is evidence which is not supporting your null hypothesis, right? So in this case, usually you're gonna, when you calculate the p-value based on your non-distribution, you're gonna get a very tiny p-value. Do you agree? So the small p-value means like the chance that your null hypothesis is true is very low. So for example, if the p-value is less than 0.05, then you're going to reject the null hypothesis and take the alternative one, right? So this is what we do in the hypothesis testing. So here I try to very briefly introduce two concepts here. In the future, we're going to talk about this in details. So since we do the hypothesis testing, and we either accept or reject the null hypothesis, then we're going to introduce two concepts here. One is a type 1 error, the other one is type 2 error. All right, so how do we understand the type 1 error and type 2 error? Because when we do a hypothesis testing, we must give the test a criteria, right? So a cutoff. So if your test statistic, in this case, if your sample mean is beyond some cutoff, then you're going to reject your null hypothesis. If your sample mean is within some range, then you believe your null hypothesis is true, makes sense, then you're going to accept it. So here, for example, we use this as a cutoff threshold. So if you look at the non-distribution here, so non-distribution here, and usually this value represented the p-value equals to 0.05. So where did this 0.05 come from? So actually, this 0.05 equals to this, the red area here. So this area, the red area under the curve of what? Under the curve of the non-distribution, right? So if you want to, if you assume the non-distribution is true, and then you can calculate the cutoff that can specify the area under the curve on the right-hand side equals to 0.05. So that's the critical value or cutoff we often use. So any test statistic falling in this region, this will lead to a rejection of the null hypothesis, right? So on the other hand, if your test statistic is lower than this cutoff, then we have a good reason to believe, yeah, your null hypothesis is true. So given the null hypothesis, you have a good opportunity, good probability to end up with a sample with the sample mean standing here, right? So this is what this is what we do in the hypothesis testing. Okay, let me share this again. All right, so hopefully this short review can remind you of what we did last time. So we have two dresses to try, right? But we do not have time to test both. So we just put one on ourselves to see if it fits us. If it is, then we take this one, the alternative hypothesis we accept. No, sorry, the null hypothesis we accept it. Otherwise, if it is too tight or too loose, we're gonna throw this away, take the other one, alternative address, without trying it. So we believe that one must fit us. So this is. Okay, let's continue. Okay, so last time I showed you these two examples here. So suppose we want to test. So this is the scientific question we want to address. So we want to test if this coin is a fair one. So if you toss the coin like 6 times and you end up with this 6 straight heads, then this is a strong evidence against your null hypothesis, right? Intuitively. And yeah, it is true because based on our null hypothesis. So can anyone tell me what is the null hypothesis here? You use the value of the parameter to tell me. So I know the null hypothesis is the coin is a fair one, but what does that mean in the language of in terms of P?
Probability is 0.5.
Yes, very good. Thank you. Yeah, that's correct. So this is equivalent to the null hypothesis, right? We believe the chance to have a tail or have a heads are equal, right? Equal to 0.5. So if that is the null hypothesis, if you believe that is true, then we don't believe this will be a likely outcome, right? So this is the rationale that we use to calculate the p-value. So based on p equals to 0.5, we can calculate what is the likelihood to end up with this outcome. So this will give you the p-value. So as you can see, the p-value will be very small, right? Less than 0.05, which is strongly against the non-hypothesis, the non-distribution. Then we're gonna reject the non-hypothesis, which means this coin is unlikely to be a fair one, right? Okay, good. Now another example. So you do the same thing, but this time you got some reasonable outcome. Like, so you got like 4 heads and 2 tails, right? And then you still, remember, we still tested the null hypothesis. This is the null model, the p equals to 0.5. And based on this, if this is true, what is the probability or likelihood to get this result? This is the p-value that we calculated. So it's good, right? Reasonable. And so which means like, okay, good. So this results outcome actually supports this null hypothesis. We're going to take it, right? So this is what we do for the hypothesis testing. All right. Now, so back to our business. So we are testing what? We're testing this guy, the R, right? I hope you still remember. So we are interested in testing the genetic map distance between two loci, A and B. And based on your data, you can calculate the MLE, the maximum likelihood estimation of this R. But sometimes you got a R equals to, let's say, 0.4. So you don't know if this 0.4 is really a 0.4, which is less than 0.5. So you want to test. So how significant this R equals to 0.4 is, right? So in another way, so actually based on your data, you hope to test the linkage between these two loci. So as so far, I think everyone is very comfortable with the first step of hypothesis testing. So based on your data, you can easily form two competing hypotheses, right? So this is one thing I require each of you to feel good about this, because in the final exam, I'm going to give you some examples, and for each those example, you need to specify the non-hypothesis or alternative hypothesis. You need to also need to specify what kind of like test is proper for each of the situation, each of the question to be addressed. All right, so in this case, we want to test the linkage between A and B, right? The loci A and B, genes A and B. And based on the cross data, either the back cross or some other cross, like F2 cross, we're gonna learn F2 cross design shortly. All right, anyway, we want to test either these two genes are completely unlinked, which means the R equals to 0.5, right? And or, yeah, alternatively, in an alternative way, so no, these two genes do not assort independently. They are linked somehow. So that's why you're gonna see the linkage between them. Then when you calculate the R, this R must be significantly less than 0.5. So this is your non-alternative hypothesis, sorry. Now, I think this is the best place for me to explain why we always put the simple things here for testing, but leaving the complicated things here. This is for our own convenience, because if you put like the simple thing here, we just need to test one thing, right? One distribution. The distribution is the non-parameter R equals to 0.5. So once we test this distribution, we can get a conclusion, get an answer for this question. However, if we reverse this two, so if we put this as a non-hypothesis, then so instead of testing only a single distribution, you have tested a lot of distribution. For example, you need to test like maybe R equals to 0.4. We want to make sure if this is true, and you also have to test whether the R equals to 0.3 and so on. So there are a lot of like distributions under these conditions, right? So that's why we are clever. We just put the simple thing here. So this only specifies a single non-distribution. We only need to test one. We only need to test one p-value based on this non-distribution. So that's why we always put the simple form in the non-hypothesis. Any questions? All right. Another thing I want to point out is like, So this actually, although there are many distributions here, but all distribution like R equals to 0.1, R equals to 0.2, and so on. So even they have different distribution, but they're all pointing to one thing, linkage, right? So so if R is less than 0.5 means these two loci are linked, but different R value means different strengths of the linkage. All right, here we are interested to test. We are interested in testing whether they are linked or not, whether they are independent or not. So that's why we put this in the null hypothesis. All right, so for testing the linkage between any two loci, so we usually use this test statistic. So test statistic is something that you can calculate from your sample. For example, if you are interested in testing the population mean, so then from this population you take a sample and you calculate the sample mean, which is something equivalent to the population mean, right? You use the sample mean to infer the population mean. Then the population mean, mu, let's say mu, is the parameter to be estimated. But the sample mean, we use the sample mean here, mu s, is the statistic. So sometimes we use X bar. So something that you can calculate from your sample is called the statistic. We use this statistic to make the inference, or we do the test based on the test statistic for a population parameter. Okay, so this is what we do in statistics. So here we use this test statistic, which is called the likelihood ratio test. And this statistic is defined like this. So is it scary? Yeah, it looks like scary, but yeah, let me explain this to you. Then after you understand this, this is super straightforward. So yeah, so don't worry about the 2 here. Don't worry about the log here. Just look at this ratio. So what is here? So here actually we are actually testing this ratio. This is called the likelihood ratio. Likelihood ratio means like the numerator is the likelihood. Likelihood is the probability that you see your data. So you see your data, for example, 4 heads and 2 tails, right? That's your data. So what is the probability that the P estimate equals to 0.7? So what is this? This is actually equivalent to this. Can anyone tell me what is this? Yeah. So this is actually the likelihood or the probability of seeing this data, given your alternative hypothesis is true. So here, if you calculated that the probability of seeing a head by tossing a coin equals to 0.7, then if this P equals to 0.7, what is the probability for you to see this data, like 4 heads and 2 tails, right? All right, so this is one likelihood given your non-hypothesis. So this is the non-hypothesis. Sorry, this is alternative hypothesis. Let me use another color too. This is your alternative hypothesis, sorry. All right, now we are looking at the ratio. So what is in the denominator? So this is also a P, but this is also a probability or the p-value of seeing your data, the same data. So this is the same data, identical data you get from your experiment. But in this case, we want to calculate the probability based on your non-model. What is your non-model? Non-model, you assume this coin is a fair one, right? 0.5. Do you agree? Does that make sense? Okay. All right. So this is exactly the ratio showing here. So this, so if you see the likelihood ratio like this, then this is equivalent to this. So what does that mean? That means like we actually compare the likelihood based on the alternative distribution versus the likelihood based on the non-distribution. All right. So suppose you got like 4 heads and 2 tails. Then you get this likelihood is very close to this one. So this likelihood ratio will give you some value like 1, right? Do you agree? Yeah, because if you got this data, so the probability for this and this should be very similar to each other. Then you got a ratio which is close to 1. And then when you calculate the log times 2, so this will gives you something like the close to 0 or something like that. So however, if you got a results like this, 6 heads and 0 tail, then can anyone tell me what happens to this ratio? So if you got 6 heads, the data, not this one. So if you do the test, toss the coin 6 times, and you got 6 straight heads and 0 tail, what would happen to this ratio? This probability will shoot up, right? You will be very high, and this one will be very low. So once you calculate this ratio, this will give you something like 1,000, which means the likelihood given this data, given the given the alternative hypothesis, the likelihood for seeing the data like this is like 1,000 times more than the likelihood given the non-hypothesis. Does that make sense to you? Any questions so far? All right, so basically we just calculate this likelihood, log likelihood ratio statistic. And if you simplify this, this will gives you this, right? Okay, so this is exactly the log likelihood ratio test statistic, lambda. And all right, so this is not required just for the, so I just talk about this as a fact. So you can take this as a fact. I don't expect you to explain why this is true, but yeah, take it as a fact. So if non-hypothesis is true here, non-hypothesis means if these 2 loci are not linked, if they are independent, then this lambda, the log likelihood ratio statistic, lambda will follow a chi-square distribution with 1 degree of freedom. And I believe everyone knows how to use the chi-square table, right? So once you calculate this lambda with your data, so you can easily look up that chi-square table and find out the critical value, and this will give you the p-value, and the p-value will help you make your conclusion for the experiment for answering this question. So any questions here? Is that clear? Okay, good. All right, very good. So this is example. So because this log likelihood ratio statistic is following if non-distribution is correct, is true. Then when you calculate the lambda, the log likelihood ratio statistic, it will follow a chi-square distribution with the degree of freedom equals to 1, right? So which means like in this case, you only need to use the first row, degree of freedom equals to 1. And this is the critical value. So 0.05, usually we use 0.05, and this is the cutoff. So if your lambda is greater than 3.8, 41, and you're gonna reject your null hypothesis. So this is the rejection area, right? Which means p value is less than 0.05. So if you got a test statistic like this, then you're gonna believe this. We're gonna believe like the null hypothesis is not true. So we're gonna take the alternative hypothesis, which means R is less than 0.5, or those two loci are linked. All right, so this is how we use this chi-square table here. Excuse me. It's very dry. Maybe I talk too much. All right. So I took this slide from one of my undergraduate genetic class, and I hope to use this slides to remind you of what we did in that class to test whether two genes are independent or not, and whether these two genes are linked or not, right? So this is the classical Mendel's experiment using the pea plants. And here we talk about like two traits. One trait is the seed color, yellow or green. The other trait is the shape of the seeds, either round or wrinkled. And we all know these two genes are located on two different chromosomes, so they are unlinked. But if we did not know this, so how can we carry out the experiment to test this, to show if these two genes are independent or not? So this is what we do here. And we start from the two inbred line, right? The double homozygous, and we cross these two parental lines, and we got this F1 the hybrid. And then we cross do the selfing for this F1 parents, and we got this sample. See, this is called the sample. Even Mendel got a lot of individuals from this experiment, but this is the collection of this individual seeds is also called a sample, because yeah, we use this large sample to make the statistical inference for the population. Actually, we are doing some tests for the F2 population, but this is only a F2 sample that we collected from this experiment. I hope you are clear with these definitions here. So this is a large sample. And when you look into this sample, you see, of course, you see 4 different phenotypes, right? Back to them, they don't know, they do not know the genotype, or they barely have the concept of the genes. Yeah, but so that's why they can only like observe the phenotypes to infer something similar to the genotype, right? So he saw these 4 phenotypes, and based on the data, the ratio of them is 9:3 to 3:1. So this is what he observed in his experiment. And then now, so then this is actually Mendel was very clever. So he just hypothesized like something like genes in pairs that control each trait, and when during the meiosis, the first law is like this two member of the pair will separate independently, and right. So this is about like one single gene. But if for 2 traits, 2 different genes, if they are unlinked, so these 2 genes will sort independently. So based on this assumption, then he clearly he can write the outcome from this cross using this Punnett square. the 4x4. And basically to form a test, so we need to know this ratio, right? So based on your data and your model, so you can form a chi-square statistic. I hope you still remember this. Chi-square statistic is the summation of I equals 1 to k. K means like a category. Here we have 4 categories here, right? And for each category, we calculate the observed number minus the expected number squared divided by the expected value. So this is the chi-square statistic. But here, the same thing, but this chi-square statistic is a little bit different from the L, the log likelihood ratio statistic, because we knew like when we use this way to calculate chi-square statistic, this chi-square statistic is following a chi-square distribution with degree of freedom equals to how many? Equals to k minus
3.
Yes, k minus 1. So it's a little bit different, but actually when you look into the details, these 2 tests will give you the same conclusion, exactly the same, but it's just different way to calculate the test statistic. I just want to remind you about this, what we have learned in the past. Okay. All right. Okay, so I think that you can easily find more information about the likelihood, log likelihood ratio test. So basically, I want to point out, so to make it more straightforward to you, we are actually comparing 2 probabilities, right? This probability is the probability. So we have already rewritten this ratio. So you see the likelihood based on the non-distribution is going to the numerator here. So here we calculate the first, we calculate the probability of seeing the data given the non-distribution, right? Theta. Okay, so now the same thing, but we want to calculate the likelihood of seeing the data given your alternative parameter here. So we just want to calculate the ratio of these 2 probability to see which one is larger, which way is larger. And this can give us the support. Based on this calculation, this will give us the evidence either support your non-hypothesis or against your non-hypothesis. And once you got a p-value, you can easily make your conclusion. All right. So this is what we do for the linkage test, right? Okay. All right. So this slide, the first part of the slides is the same. So this is what we have just learned about the likelihood, log likelihood ratio test statistic. And since the degree of freedom for this lambda is 1, then from the table, we can easily see like the critical value for p equals to 0.05 is 3.841. All right. But in quantitative genetics, sometimes like this value looks very weird. It's not very easy for us to use for a test. So instead of using the lambda, we use something called the likelihood odds, the log, the lot value. So lot value, yeah, I kind of forgot the full name of this. This is the lot score. Lot score actually is a another statistic which is transformed from the lambda. All right, as you can see from here. Okay, lot score. We, instead of using the, let me erase this. So instead of using this form, we just use this. This is the natural log. Okay, we use the log base 10 transformation for this ratio, the likelihood ratio, and then so this is the derivation. So this is not required, but you need to know there's a association between this log score and the likelihood ratio test lambda. All right, the relationship is like this. All right. And so the log score, the log score is actually equals to this. And this is it is very convenient for us to use this log score for testing. Why? Because we can use some like integers here to help us to do the test. So conventionally, we use this cutoff, the log score. If log score is greater than 3, then we assume the linkage between two loci, A and B, is significant. So this is what we commonly use for the linkage test. All right. Any questions here?
So is this graph just a little bit more narrow than the LRT?
Yes.
Okay.
Yes, I think it's more. Yeah, that's correct. So this criteria is actually more stringent than using this cutoff, right?
Okay.
Yeah, because yeah, this is a good question. We in the future we're going to talk about this. Why in quantitative genetics, why we usually use a more stringent criteria for testing? Because this is for just the testing a single pair of genes, right? 2 genes. But in reality, so usually we deal with like multiple genes or multiple pairs. So that will involve like something called in statistics called the multiple comparison. So when you do the multiple comparison, so it is easily for you to make the test the statistic inflated, right? So you're gonna make the inflated type 1 error. So that's why we try to control that type 1 error. So don't worry, I will talk about this later. If you want to control the family-wise type 1 error, so sometimes you have to use a very stringent test for each test to test each pairs, right? So if you use a more stringent criteria to test each gene pair, then overall you're not gonna worry about like family-wise type 1 error being inflated. Yeah. Okay.
Thank you.
Sure. Good question. So yeah, so this is usually, yeah, in a lot of papers or in the future when you use some software to do the test, linkage test or whatever, or even the QTL mapping in the future, you always see people use this, the log score. So because it doesn't matter for a statistician, either use this or that way, it's the same. But for some like people who hate statistics, they would like to use something like this. It's easy for them to explain, to interpret like their results. So they use like, oh, a log score greater than 3. Oh, this is a statistically significant linkage. Yeah, I take it. Sometimes it's troublesome for them to memorize this weird numbers here, critical values. Yeah. Okay. Yeah, statisticians are always like make client happy to develop some like easy ways for them to use the tools. All right. Thank you. All right. Any questions before I move forward? So I think I'm done with the backcross design, right? So let me give you a brief summary. So backcross means like we have 2 parents and we crossed the 2 in bright line, we got F1, right? And once we got the F1 progeny, we just cross this F1 back to one of these 2 parents. Then that's one possible design in breeding. Now this is another design commonly used, and this one I will show you why this one is more powerful than the back cross. So the F2 is more powerful in terms of statistic power. This one F2 design is better than the back cross design. All right. So this is how we design this experiment. So we also start from 2 implant line parents, and we got the F1, the dihybrid. And instead of going back, cross back, so we just do the cross among this F1 progeny, and we end up this. So you're gonna see we have more variability here, right? So in the back cross design, we only see 4 categories, right? But in the F2, we see more than 4 categories. So some can be combined. I'm going to show you because some categories. So initially there's like 16 categories, right? But if you combine the progeny with the same genotype, they can end up with less than 16 categories. But at least the number of categories for F2 design is greater than 4, right? So we see more variability, which means like we have more resolution. Do you believe that? We have more resolution given the same sample size. If you do the F2 design rather than the backcross design, we got more resolution, which means like we gain more statistical power for testing the linkage for these 2 genes. Does that make sense?
Okay, I think I might have missed it. Can you repeat why it has more power?
Oh, okay, sure. All right. So first, if you want to, so like the TV. So when I was little, so the TV like with very little like resolution, but now high definition, right? You can see the graphs like more sharp and clearly, right? Because of the resolution. So the same thing here. So if your budget can only afford this many samples here, so you can choose like do the backcross design or the F2 design, right? Either way. However, the backcross design only gives you like 4 categories in the progeny, but the F2 design will give you more than 4 categories. So intuitively, like you can see more things, variability, or in another way, you got more resolution in your data. Then this will help you gain power to do the statistical testing. Does that make sense?
Yeah, that makes a lot more sense. Thank you.
Sure. All right. So yeah, the same graph here. So I just want to show you. So this is exactly the F2 design, so in this specific example, the Mendel's experiment, these 2 genes are actually unlinked. So that's why you're going to see this ratio, right? The 9:3 to 3:1 ratio. However, if this is not the case, suppose like we want to test the 2 other genes, and these 2 genes are located on the same chromosome and they are closely related to each other, they're linked. So you're going to see different ratio, right? Here, you're going to see different ratio. And the ratio will tell you about how tightly these 2 genes are associated with each other, right? So this is what we do here. So, but basically, we're gonna using this design, F2 design. We're gonna be able to use this Punnett square, the 4x4 Punnett square, to describe the possible outcomes from the possible genotypes of the progeny from this cross, right? Okay. All right. Now, because we want to do the statistical analysis. So usually we need to transform this beautiful graph into this beautiful tables because we are dealing with numbers. So tables sometimes are more useful for us to help us to write the equation, the formula, and to do the test. All right, this is the same with the previous slides. The graph, the Punnett square. This is also a Punnett square. So suppose this is one F1 parents. Let's say this is female parents. and this is another parent, F1 parent, male, because they're both F1 progeny. So for each of parents, they can produce 4 possible gametes, right? So this is 4 possible gametes from this parent, and the same 4 possible gametes. These 2 parents are actually equivalent. All right, and because remember here we're talking about 2 genes A and B, and these 2 genes are no more independent; they are linked. So how do we denote? What can we use to denote the linkage between this A and B? Use something we have learned. Can we use R? Yeah, we use R to represent the linkage between A and B, right? If this R is less than 0.5. Now, I hope to remind you, so this R is actually a probability. And in the first chapter, we talk about this a lot. So this is called the recombination fraction. And also it represents the probability of having crossover, right? Linear recombination. This R is a probability value, which is a value greater than 0, but less than 0.5. Okay. Okay, so now suppose look at this parent. So can anyone tell me why the probability for the first parent, why the probability to having this gamete, big A and big B, equals to this? Why? That's the probability of having this gamete genotype.
Because it's a parental type?
Yes, yeah, because this is the parental type. There's no crossover. So the R means the probability of having a crossover. Then reciprocal, I like this term. I know, yeah. So we use 1 minus this. This represents the probability of having a parental type, right? But if we got 1 gamete like this, we must get another gamete by symmetry, right? So that's why for each of these 2 parental type, we multiply this 1/2, right? Does that make sense? That's the probability. The same thing here. So this R represented the probability of the non-parental type. If you got a gamete of this genotype, simultaneously, you're going to get a genotype like this, right? The gamete. Okay. All right, perfect. Any questions here? So this is important. We need to understand this. Why? So this is the genotype of the gametes, possible gametes, and this is the probability that is associated with each type of gamete. So we must understand this. In the final exam, probably I can give you some problem like this. I give you this situation, F2 cross design, and I will ask you to write this table for me. And so you have to write the genotypes, that is, and the associated probability, the same thing for this parent. And also you need to give me the possible progeny from this cross and the associated probability. So this is the key thing we need to pay attention. Any questions? Okay, now, so we consider like randomly randomly each of these gametes from one parent can come together with any like gametes from the other parents. Then we can randomly generate this 4x4 Punnett square, right, table. And for example, if this gamete comes together with this gamete, then the F2 progeny will be like this, right, the genotype. And this is the probability for that progeny. Why? Because since independent, so we're gonna multiply this probability by this probability. We got this. So then easily you can get this, right? So the same thing. All right. All right, so this is the model. So this table actually gives you a model. And based on your model, you can do your experiment. And in your experiment, you can get some realized data, right? Realized data. the realized data from your F2 cross experiment is called the sample. So no matter how large your sample is, that's a sample. So large sample or small sample, they are all samples, sample from your target population. So here you are targeting the F2 population from this cross, and this is your sample data, right? And so in your sample, suppose, so for each genotype, suppose you can distinguish each progeny, each progeny category, then you're gonna see, so this is not true. So sometimes, because for some categories, they are undistinguishable. So that's, for now, let's assume that you can clearly find the number of the progeny for each of the 16 category, okay? Yeah. And those are the data. So those data means like, so in your F2 experiment design, so you end up with these 16 numbers. So each number represents the number of progeny in this category. Does that make sense? All right. And this is very similar to what we have dealt with, right? So we use this data. We can easily calculate the log likelihood function, right? Because we have our model, and this is our model, and we use this model and use this data. We can easily calculate the log likelihood function, and then you can easily derive the maximum likelihood estimation to estimate this guy. So this is what we want to estimate, right? The R. Okay, because we want to calculate, we want to estimate this R, and also we want to test whether this R is less than 0.5 or not, right? And after that, once you got a p-value, then you can easily make your conclusion. Oh yeah, these two genes are linked. Or oh no, these two genes are unlinked. This is what we do. Okay, so a little bit more complicated here. So this is compared to the backcross design, of course. So when you do the F2 design rather than the backcross, you gain some power, but on the other hand, you have to spend more your brain power, yeah, to develop a more complicated formula here. So this is how we calculate the likelihood. So given the probability for each of the 16 categories. So I hope every one of us can understand what I mean here, the probability ij here. So this is the value showing here. So we have P11, P12, P21, something like this. So we have 16 probability values that are associated with this 16 category, right? Okay, so when you want to construct your likelihood function, this is what we do here. So 4 by 4, 16 terms, right? For each one, so we calculate the original likelihood is something like this, ij, but we hate to deal with the product forms. We want to do the summation form. So that's why we use the log. If you do log, then this will become easier here, right? Something like this. Does that make sense? Okay, so this is how we calculate the log likelihood. And if you simplify this using the numbers that I have shown in the previous slides, so I hope you can link the previous slides with this one. So those are the numbers we're talking about. That's the data, right? The realized data. So with your F2 experiments, you're going to end up with these numbers. Those are the data. And using this data and the model, you can easily rewrite this into this. Any problems here? Any questions? So this might be part of your final exam. So I'm going to show you the table, and I'm going to ask you to write this log likelihood function for me. All right. Okay. Now, the rest of the steps are very similar to what we have learned last time, because this is the log likelihood function. And we try to, because here we want to estimate this R, right? And we want to identify the optimal R, which can maximize this log likelihood function. Because only the correct R estimation will gives you the maximum probability of showing this data, right? Does that make sense? So then we do the MLE. So this is what we have learned last time. We just do the first derivative of this guy, right? So this distribution should be something like this. And if we do the first derivative and set the first derivative of this function equals to 0, and this will gives us the slope of 0 for this curve. And this slope 0 actually identify the R hat, which can maximize your log likelihood function. Does that make sense? Any questions here? So this is always what we do. This is always what we want to do to find your MLE. You do the first derivative of this guy. So just simplify this. This is easy, right? You do this and do this, and you set this equals to 0. Then you do a little bit like not very complicated algebra. You can end up with this. Okay. And after that, you do the second derivative of your score function. So this is the B function or H function, and then you can get this. And we have learned this. This is called the information of this estimation, and this gives us the variation of the estimation of this parameter R. Right? Yeah. All right. This is what we do for the MLE estimation. And we also want to estimate the variance of this estimation. Okay, any questions here? So this slide is very important. And I think it's reasonable to put a question like this in your final exam. And I may give you a little bit like change the form, so different notation or things, but the reasoning behind is the same. And you need to show me the likelihood, correctly showing the likelihood function. And you need to do the score function, the first derivative of the likelihood, and set this to 0 and solve the equation. You're gonna get the MLE. And after that, you just go further step to do the second derivative and get the variance of this estimation. Then you got the scores. So in the final, so you're gonna do this step by step. In case like you did all right in the previous steps, but finally in some final step, you got some wrong answer. That's fine. So, but please show every steps. Please show every steps in your derivation. So even you got the final answer is not totally correct, you still got a majority of the points for the previous steps. Okay.
Did Dr. Jia freeze?
Yeah, I can't hear.
Yeah, he's frozen too.
Okay. Very good. All right. So this. Yeah, go ahead, Adrian.
Oh, sorry, Dr.
Can I hear you?
You
Could you say that again?
you froze for the past like minute or two.
Oh, sorry. Maybe
Yeah,
my
can you
Wi-Fi.
just repeat?
Let me double check my Wi-Fi. Sorry. Give me a second. My Wi-Fi is okay. So sorry about this. what was the last sentence you you heard from me?
Can you repeat like the past like 30 seconds or something?
Let me see.
So you just emphasize to show our steps.
Okay, sure.
Um,
So in the final exam, I likely give you a question like this. So for example, I give you a design. So F2 design. So tell me what the F2 design is, and why this guy is better than the backcross design. So I will talk about this shortly. And if I give you a table, so if I give you a question about the F2 design, so probably I will ask you to write this table for me. So that's the possible. That's actually the model. And given the F2, so you are supposed to see the 16 categories with this definitively defined probability for each category, right? So you need to know this. And if you have the data like this, so this will be given to you. And then, so what you need to do, so what I expect you to do is like, you can write this. This is the general form of the likelihood. And based on your data, you're gonna be able to rewrite the likelihood like this, right? You just plug in everything and got this simplified formula like this. And this is your likelihood function, log likelihood function. And if you want to derive your MLE, then the next step you need to go is to do the first derivative for this one. And once you have this, set this equal to 0 and solve this equation, you got this. This is your MLE, right? And after that, you need to do one more step to do the second derivative. And this will give you some information about the information matrix, which can be used to derive the variation of your MLE. So this is your MLE, and you always want to calculate the variance of this MLE, because this can tell you how accurate your estimation of the R is. Okay. All right, now, yes. So if I ask you why, please tell me why your F2 design is better than the backcross design. So given the same sample size, so suppose you so you got some like grant from NSF to do the experiment, you can only afford like this many samples. So this is the accuracy, estimation of the accuracy you can achieve. So with the same number of the N plus, the capital N, so the variation of your estimation, this represented the error of your estimation, right? The error of the estimation from the F2 design is half of that from your backcross design. So this is why, as I said, because F2 design actually will generate a progeny pool with larger variability. And this larger variability in this test sample will give you more resolution or statistical power for your testing. So is that clear?
Yes.
Okay, very good. All right, so all right, so let me see. Let me think if I should continue this or not, because I probably I'm gonna stop here. So at the beginning, as I said, I try to move it forward slowly to give you more time to digest, because this is a little bit different, because as I mentioned in the 4x4 table, so we assume that we can differentiate each categories definitively, right? But in reality, sometimes this is not possible because if you look at here, if you look at here, this category, let's say the 1, 3 and the 3, 1, the genotypes of 1, 3 and the 3, 1 are identical. So you just do not know so which gametes from which parent, right? So in the reality, these two may be mixed together. So the example I just showed you, that's an ideal situation. So suppose you can differentiate all of them, then that's easy step. That's the easy case that you can deal with. But in reality, in most of the cases, so you got data like this. So for example, the 1, 2 and 2, 1, they are mixed together. So you only see the sum of these two categories, right? And so the diagonal category, that's easy. So you can use easily like differentiate these 4 categories from the rest of the categories. But for some of the categories, they are sum or mixture of multiple categories. So in reality, for most of the situation, you only see like 9 categories rather than the 16 categories. Does that make sense? Okay. So, but yeah, I know like sometimes life to statistician is quite difficult, but you have to face. You need to be brave. So we call this like sometimes we call this like using the observed data. So we don't use the ideal data. Sometimes we have to face the reality. We use the observed data here. Okay, and then we probably need to modify our model and our likelihood function a little bit. But I'm gonna stop here because I don't want to confuse you. So we're gonna talk about this next time. But yeah, make sure when you have time after class, just go over the previous slides to make sure you understand those steps. Those are the key steps. That's why I move very slowly. In the future, when everybody are comfortable with all these solid concepts, then we can easily move very fast. So I don't have to spend a lot of time on a single point like this. But in the future, yeah, if you knew those points, so we can learn the advanced stuff like very quickly. All right. So I'm gonna stop here for today, and so we have like probably 10 minutes for the class, and so if needed, we can also use another like 15 minutes, 20 minutes for discussion, answer your question. So any questions so far for?
I had a question.
Yeah.
Comparing the backcross and the F2 design, is a backcross in practice maybe easier because you're dealing with less numbers of? Okay.
You're right. You're right. There's a trade-off, right? Because sometimes like you pay more, then you get more. You pay what you get.
Yeah.
So of course, yeah. If you want to get this thing done quickly and in an easy way, yeah, backcross, probably blessing you. And yeah, but if like so that's a good question. So sometimes like even for our dissertation or projects, so we need to like do it very smartly, right? So if you do not know this is the right direction, so you start with a pilot study using the small like backcross design to see if in this pilot study give you some like good idea, good feeling about the direction. And once you confirm, yeah, that's the right direction, so probably you're going to put more money in your study and do a better design and get more resolution. And then, yeah, then you can get convincing results for publication, for great publication. Otherwise, yeah, you cannot publish your study like in very high end.
Sure, makes sense. So you do backcross first, just for a general
idea. So sometimes like so before you form your idea about your dissertation, so you need to explore different possibility, right? So you try here and there a little bit, then so you can use simple and the cheaper way. But once you find some like hopeful direction, yeah, put your money or your money there. Yeah.
Thank you. It makes sense.
All right. Any other questions?
I have one, which is, do you know how many? Do you have an idea how many questions are going to be on the midterm and final? I know it's a far time from here, but it's just that you say that
Mhm.
like this is going to be on the final and that's going to be on the final, and I had the impression that it was going to be like 10 questions, but they're going to be really hard, and now I'm not sure anymore.
Yeah, usually like I put like about like 10. So, but so of course, so we will cover a lot of topics through this quarter, right? But finally, I'm gonna pick like several. But the 10 question doesn't mean like 10 solid like big questions. So maybe sometimes like some questions is like the nested question. So I will give you like for example, the F2 design. I will ask you first, what is the F2 design? You just give me the definition, and what's the difference between F2 and the backcross? Yeah, so you can at least get the first two parts, right? That's easy part. And after that, I will ask you the third parts. So show me the Punnett square, the table, and for the possible outcome progeny from this cross. And for each category, you need to show the expected probability, right? Given the R. Yeah. So that's the way. So if this kind of like question, if each question contains like multiple steps, so maybe I will reduce the total number of the questions. So it depends. So it depends. I cannot give you an exact number now, but usually like something like the qualify exam. So at the second year, at the end of the second year, so the qualify exam is like that. So sometimes I give my student. So if I'm on a committee, I give the student like maybe 4, 5 big questions. But for each one, you're gonna see multiple steps there. Yeah, something like that.
Okay, thank you.
Sure. Okay.
I just had a quick question. Does the 0.05 p-value only work with a normal distribution?
Good question. No. So this is like kind of like the rule of thumb. So normal is the one that you often see right in different situations. But for chi-square, let me show you. For chi-square, we still use this. This is kind of like the rule of thumb. So I think I have a slide here. So this is a chi-square distribution. Also, we use this 0.05. So that's why you see this, right? And so this is the basic part. So when you only do a single test, for example, you just test one gene. If this gene is highly expressed in tumor, let's say cancer, versus the normal, that's a single gene test, right? Then so either a normal distribution or some other distribution, let's say chi-square, we just, for simplicity, we just use conventionally, we use this as a cutoff. But this is not the case we do. Like right now, like we handle like high throughput data, right? So we survey like many thousands of the genes at the same time. So we're gonna gene 1, gene 2, gene 3. So we do this multiple comparison. Then of course, this cutoff is too much relaxed. So it will cause a lot of problems. So we're going to talk about this. So when we do the multiple comparison, we have to use a more stringent cutoff to make sure the family-wise, the overall type 1 error is being controlled. All right. So in that case, you're going to see. So I think 2 years ago, I published a paper with some colleagues talking about how we choose different cutoff when you do the whole genome wide association study or comparison. So depend on the selection of the criteria, proper criteria, depend on the number of tests. How many genes are you testing, or how many loci are you testing? So depending on those, you're gonna probably choose different way for testing. Yeah. This is the most general common thing for single test. Yeah, not only for normal distribution, for all kind of like distribution. Is that clear? Good. Thank you. All right. So any other questions?
Yeah, I have another one. Does it mean anything if the p-value is closer to 1? I mean, I know it means that's not statistically significant, but like, is there really a difference between p equals 0.2 and p equals 0.9?
Yeah, so that's a good question. There's a lot of debating in statistics. So I can say, like, in terms of testing, the 0.05 cutoff, there's no difference because either your p-value equals to 0.2 or 0.8, they will give you the same answer, right? You're gonna accept the null hypothesis. But I agree with you. So different p-value will give you a different confidence to take your null hypothesis. So if you got a big one like 0.8, so you will be very happy to take your null hypothesis with no doubt, right? But yeah, if your p-value is kind of like marginal, like approaching to the significance level, like 0.06, what should I do? So this will give you a lot of like suspicion. So I agree. So maybe you should we should follow like Mariano's like suggestion. So if you got a 0.06, so you're gonna spend more money to redo the experiment to make sure the next result gives you the same conclusion. You have so big p-value, you don't have to repeat your experiment, but the small p-value which is close to 0.05, you have to do it again to make sure the first trial makes sense. Yeah.
All right, thank you.
Sure. All right. Any other questions here? Okay. I hope all of you enjoy the class. Yeah. All right. Okay. See you next time.
Thank you.
Bye. Sure. My pleasure. Bye.